We take many things for granted these days, but as a materials engineer, I have always found it incredible how much we take materials for granted. Everything we build is dependent on these materials. They are so significant that we've named entire periods of human history after them, from the Stone Age to the Space Age. They have all been made possible by the materials we have at our disposal and our mastery over their properties. I've spoken about aluminium and silicon before, but today we're going to talk about one of the most influential periods in human history, the Iron Age. Some of the earliest evidence of iron being used as a material goes back as far as 3500 BC in Egypt, where beads of iron taken from a meteor were found. Meteoric iron was a highly prized material due to its heavenly association. Tutankhamun was buried with a dagger made of the material, but meteoric iron was the only naturally occurring source of iron at the time because iron reacts readily with oxygen to form iron ore. There is no oxygen in space, so meteors delivered this material to Earth in a form humans could use without having the technology to extract it from its ore. The Iron Age began at various points across the world as humans started to learn how to extract iron from its ore, and its end date varies between regions too. In Britain, the Iron Age began in 800 BC and ended when the Romans invaded in 43 AD, marking the start of the Roman Age. If we continue to define human history by the materials being mastered at that time, I would argue that the Iron Age lasted right up until a little over 150 years ago, when steel was first mass-produced. Now, while this era is called the Iron Age, the best materials at the time were made from steel. You may not have known, but iron and steel are mostly the same material. Before we go forward, if you haven't seen my Material Properties 101 video, the words in this section may confuse you a little. If you haven't seen it yet and don't have a background in material science, I highly suggest you pause and go watch that first. So the main difference between iron and steel is the amount of carbon they contain. Anything with a carbon content above 2% is cast iron. In general, a higher carbon content results in a harder and less ductile material. Cast iron has a very high carbon content, which makes it very hard but also very brittle. As iron started to become more popular, more and more of the early bronze cannons were replaced with cast iron, as it was cheap to manufacture and could be fired more often without being damaged. But these material properties meant that cast iron cannons had a tendency to explode with no warning, making them dangerous to operate. Cast iron is not suited for structural use either. In fact, its use in bridges in the mid-19th century led to a series of bridge collapses. Later, these bridges were rebuilt using wrought iron. Wrought iron contains less than 0.8% carbon, which makes it a much better material for applications like this, as it is ductile, allowing it to bend under loads without breaking. But it has a low carbon content, which makes it a lot softer than cast iron. Steel is between the two, with a carbon content between 0.8 and 2%, giving it an ideal balance between hardness and ductility. The history of iron is defined by our ability to control that carbon content. Iron is the fourth most common metal on the surface of the Earth, just below aluminium, but it reacts with oxygen readily to form iron oxide ores. Rust is one form of iron oxide, and preventing it is a constant struggle in structural maintenance. The Eiffel Tower has been painted 17 times since its construction to protect it from that corrosion. Every 7 years, about 60 tons of paint is applied to the Eiffel Tower, and the colour of paint has changed over the years. The tower was originally a Venetian red, and has changed a few times from a more yellowish brown to a chestnut brown until the adoption of the current specially mixed Eiffel Tower brown in 1968. Because iron reacts so readily with oxygen to form iron oxide, iron does not exist on the surface of the planet in a usable form. The first step to process iron is to remove that oxygen. In the mid-Bronze Age, the first signs of production of iron are seen. Most of this early iron was smelted in these furnaces called bloomeries. One of my favourite channels on YouTube, Primitive Technology, actually created a miniature version in one of his videos. These bloomeries heat the iron ore, using charcoal as a heat source. The burning of charcoal produces carbon monoxide, which reacts with the iron oxide in the ore to form carbon dioxide and iron. The bloomery is heated above the melting point of the impurities but below the melting point of iron, and so, as the fire rages, material falls to the bottom of the bloomery and the heavier iron consolidates at the bottom, while the impurities form a molten pool called slag, which can be drained away. Another great channel on YouTube, How to Make Everything, made a series about this process. When the iron is removed, it is in the form of this porous mixture of impurities and iron. It needs to be worked with a hammer to consolidate the iron, while the waste material is beaten off. The material left over is wrought iron, which, as we discussed before, has a very low carbon content. These bloomeries produce very small quantities of iron, especially before the water wheel was introduced to drive the bellows. which allowed the bloomery to grow in size while keeping the temperature high enough. Despite the small quantities it produced, the bloomery revolutionized human life, even beyond the obvious military advantages of iron weapons. Iron ore is much more common than the copper and tin that spurred the Bronze Age, allowing iron to be produced in many areas. These communities could make their own tools and weapons without having to import the material from abroad. Iron ploughs are stronger and heavier, allowing farmers to plough their land quicker and thus grow more food. A single farmer could feed more people, allowing more people to dedicate their lives to different trades. Society was becoming more stratified and trade was increasing, and things began to accelerate even more as we discovered better ways of extracting iron, like the blast furnace. Blast furnaces increase the production of iron dramatically. The blast furnace gets its name from the method that is used to heat it. Preheated air at about 1000 degrees Celsius is blasted into the furnace through nozzles near its base. Blast furnaces do heat the iron above its melting point, along with flux materials. A flux is a chemical that will combine with the impurities, allowing them to be extracted easily. In this case, the iron ore is mixed with limestone and coke. Coke is a refined form of coal, with very little impurities, and it works similar to the charcoal in the bloomeries by producing carbon monoxide when burned, which in turn reacts with the oxygen in the iron ore to remove it, as shown before. The heat from the process decomposes the limestone into calcium oxide and carbon dioxide. The calcium oxide then reacts with the silica impurities in the ore to form calcium silicate. This, along with other impurities, form a liquid layer of slag that floats on top of the heavy molten iron, which can be drained away, while the heavier molten iron is tapped lower down. This method allowed vast quantities of ore to be converted to iron quickly, but it has a drawback. At higher temperatures, iron readily absorbs carbon, so the iron created in blast furnaces had a very high carbon content, making it cast iron. So an extra step is needed to decrease the carbon content. This is called fining. There were a number of ways of doing this. One way was in a refinery, where the cast iron is heated back up, which oxidizes the carbon. The material would then be beaten with a hammer to knock the oxidized carbon out of the material. This process would be repeated until wrought iron was produced once again. Producing steel with this method would have required incredible skill, but there were methods of producing it in small quantities. Almy demonstrated one of these when producing crucible steel, which was produced by mixing wrought iron and cast iron in a sealed crucible, which prevented carbon from the air from entering the material. When mixed, the low carbon wrought iron and the high carbon cast iron would form steel. The puddling furnace was another method of production that involved heating the cast iron in a furnace that separated the fuel and the iron. The heat from the hearth would then radiate through the furnace and liquefy the iron. As the iron became molten, a worker would then stir it to encourage the oxidation of impurities. All of these methods of production were fuel and labour intensive, making the end product too expensive for general industrial use. And the average life expectancy of a puddling furnace worker was just 30 years old due to the toxic fumes produced. With the expansion of the railroads in the early 19th century, the pressure to develop a faster and cheaper method was growing. All our modern rail tracks are made from high-strength steel. Its superior hardness over wrought iron allows it to resist wear. This is a difference between a worn steel rail and a new one. This kind of wear happened so quickly with wrought iron that certain sections of popular lines needed to be replaced every 6 to 8 weeks. Steel also has a superior strength over wrought iron, allowing it to carry more load. If you watch my last video, you'll know why this shape helps the rail carry even more load. So we can see why finding a method of mass production was so important, and this is where the British metallurgist Sir Henry Bessemer came in. Bessemer designed a converter that looked like this. Molten iron was poured in here from a blast furnace, and hot air is passed through the bottom. The oxygen in the air oxidizes the impurities in the iron. The carbon reacts to form carbon monoxide, which is expelled as a gas, while the silicon and manganese oxidize to form a layer of slag. This process was very fast. In fact, early on it was a victim of its own efficiency, as it removed too much carbon and left too much oxygen in the iron. To combat this, another alloy that I am definitely about to pronounce wrong, containing iron, carbon, and manganese, called Spiegeleisen, was added. The manganese would react with the oxygen to remove it, and the carbon increased the carbon content as needed. But it had another problem in the early days. The process did not remove phosphorus from the iron, and high concentrations of phosphorus make the steel brittle. So initially the Bessemer converter could only be used with iron obtained from ores with low phosphorus concentrations, which were scarce and expensive. This problem was later solved by Welshman Sidney Gilchrist Thomas, who discovered that adding a chemically basic material like limestone to the process would draw the phosphorus into the slag. This availability of cheap steel caused an explosion in growth in the rail industry. Steel is so vital to our daily lives that it is often considered a measure of of economic success of a country. A high production of steel means a high demand for steel. A high demand for steel means your country is building infrastructure. For example, this is a graph showing China's steel production from the 1990s to present, showing the rapid rise of China as a global superpower during their economic reform. Without steel, our buildings could never have grown to the heights we see today, and bridges like the famous Golden Gate Bridge would have never been possible. There is even more to learn about steel's fascinating history, like how the expert blacksmiths of Japan managed to create the katana, and they learned how to carefully control the crystalline structure of the steel to forge the perfect blade. But we'll talk about that in another video.